Welcome back to the deep dive. Okay, if you're maybe an engineering student thinking about the rail sector, or perhaps you're just starting out on a big infrastructure project, or maybe, like me, you're just fascinated by how these massive systems are kept safe and running. Let me ask you this. What's the absolute number one thing you have to do before you even think about track design, or coding signaling software, or, putting a shovel in the ground?
It's a great question. Most people, their first thought is technical.
Yeah.
Performance, specs, materials, maybe the schedule. But the real answer, the bedrock, it's establishing the governance, the proof, really, that this system is safe. And that comes before any design is locked down.
Exactly. And that's System Safety Assurance, or SSA. For a long time, I think SSA was seen as, well, almost an afterthought, just some paperwork you did at the end, a regulatory thing.
Or a box-ticking exercise.
Yeah, but we need to flip that thinking. SSA is actually, it's the backbone. It's this essential framework providing the governance, the processes you can actually check, and critically, the objective evidence. You need that proof that whatever you're building or changing a product, a whole system, even just an organizational tweak can be integrated, operated, and maintained safely.
And what's really interesting, I think, is how SSA forces that safety conversation right up to the top, to the leadership, right when a project is just an idea. It pulls safety from the back end, makes it the central pillar for every technical choice. Honestly, if you don't have that SSA framework sorted up front, you don't really have a viable project.
So that's our mission today, a real deep dive into that starting line. We want to give you a shortcut to understanding those foundational bits, the legal responsibilities you just can't pass on, and the technical integrations you absolutely need for SSA before things get rolling. This is the context, really, that you need to get your head around to do well in any safety-critical field, especially rail. Okay, let's start with the big picture philosophy and law. Because when you talk about making decisions about safety risk in rail, there's one acronym that hangs over everything, from the CEO right down to the person working on the track: SFERP.
SFER, so far as is reasonably practicable.
Right.
And SFERP isn't just a, nice idea. It's the absolute cornerstone of modern safety law, and it has real legal teeth. It basically says any risks from rail operations. First, you have to try and eliminate them if you possibly can.
Eliminate them completely.
If possible, yes. But, okay, if elimination is genuinely impractical, like, say, the only way to eliminate a tiny risk is to shut down the entire network, which isn't feasible, then you have to minimize those risks, get them down to the lowest level you can achieve.
And this is where it gets tricky, right? That's where the engineers and the managers really earn their stripes, because reasonably practicable isn't just gut feel.
Not at all. It forces a calculated, evidence-based decision. You've got to weigh things up. The benefit of reducing the risk, how much less likely is an incident, versus the cost, the time, the sheer effort involved in putting those controls in place.
It sounds like a balancing act.
It's exactly that, a tightrope walk. And you can't just wave something away as too expensive if the risk left over is still high, potentially catastrophic. The responsibility, the burden of proof, it always sits with the duty holder, usually the rail transport operator, the RTO. They have to prove that doing more, even if it was costly, wasn't reasonably practicable given a level of risk. It flips the usual thinking you have to justify not acting.
Okay, so this core principle, SFARP, it's then written into law, into a kind of unified rule book.
Exactly. Often under something like the Rail Safety National Law, or RSNL as it's known. This kind of legislation creates a standardized, consistent approach to safety regulation across the board, which is vital in rail because trains, well, they cross borders all the time.
Makes sense.
And the RSNL, it doesn't just list rules, it sets out the formal legal duties that land squarely on the operators. And here's something really crucial for anyone working in this space. These duties for the rail transport operators, the RTOs, they are non-transferable.
Non-transferable meaning?
Meaning you can delegate tasks, sure, you can hire consultants, you can outsource design work, but you cannot legally pass the buck on your fundamental responsibility for the safety of the whole system. It stays with the RTO.
Let's break down those duties a bit. What are we talking about specifically?
Well, there's a general duty of care that covers employees, workers. It often lines up with general workplace health and safety laws. But the second duty, that's the really expansive one, a duty of care to all persons who might encounter the rail assets.
All persons. That sounds incredibly broad.
It is. It means passengers, obviously.
Yep.
But also contractors working on the line, pedestrians at level crossings, even people whose property borders the railway. It's a huge scope.
Wow.
And the main obligation that flows from that duty, it's the need to proactively demonstrate. And that means hard evidence that you've identified all the safety hazards you could reasonably foresee, and you've either eliminated them or minimized them. SFOP. You need that audit trail. Proof you did your due diligence.
So the law is the SFO principle and the duties. Who actually checks if the operators are doing this? Who enforces it? That must be the national regulator.
That's their role. But it's important to see them as more than just the police force waiting to hand out fines. Their job is broader.
Okay.
Yes, they administer the accreditation system for RTOs. That's the license to operate, essentially. They monitor compliance. They investigate incidents when things go wrong. But critically, they also provide education, training. They try to lift the overall safety standard for the whole industry. They actually want operators to succeed safely.
It sounds almost like a partnership. Is that what people mean by co-regulation?
Precisely. It's often called a co-regulation approach. The idea is the regulator relies on the RTOs, the duty holders, to manage their own risks first and foremost, using their internal know-how. But the regulator keeps that oversight power, making sure everyone's playing by the rules and meeting the standard.
But isn't there a potential conflict there? If responsibility is shared, does accountability get a bit fuzzy? Could an RTO be tempted to just, wait for the regulator to tell them what to do, kind of letting the fox guard the hen house, so to speak?
That's a really sharp point, and yeah, it's a constant tension. But the safeguard against that fuzziness is that non-transferable duty we talked about.
Ah, okay.
The RTO always remains solely responsible for proving SFERP. The regulator's job is essentially to audit whether the RTO's own systems for doing that are effective. If something goes wrong, and an RTO's safety management system is found lacking, the legal buck stops entirely with the RTO. Doesn't matter how many workshops the regulator ran. It forces that internal ownership.
Okay, so the law provides the why, that non-transferable SFIRP duty. But how does an RTO take that huge legal thing and turn it into actual, physical, demonstrable safety on the ground? This must be where the safety management system, the SMS, fits in.
Absolutely. The SMS is basically the organization's safety Bible. It's the comprehensive plan for how they manage safety day to day. And SSA, System Safety Assurance, it can't be separate. It has to be woven right into the fabric of that SMS. It's how the RTO provides that clear, auditable proof that they actually have the competence, the capacity to manage the risks involved in running a railway.
What are the key things an SMS absolutely has to cover? It can't just be a nice document sitting on a shelf.
No, it needs to be active. There are really 4 critical functions. First, you need solid processes for identifying hazards and assessing the risks they pose. Second, you need systems to actually implement the controls for those risks, not just talk about them.
Right, doing something about them.
Third, you need ongoing monitoring of safety performance. That means collecting data, tracking metrics, seeing how you're actually doing. And fourth, there has to be a mechanism for continuous improvement, learning from near misses, incidents, audits, and feeding those lessons back to make the system safer over time.
That sounds like a pretty hefty system to build and maintain. And you have to prove all this before you even get the green light to operate. What does an RTO actually have to show to get that accreditation?
Yeah, the accreditation hurdle is high, and rightly so. RTOs have to demonstrate quite a few core capabilities. They need to prove they have the competence and the capacity to manage the specific risks of whatever they plan to do, whether that's running heavy freight trains, a city light rail network, or high-speed passenger services. The risks are different.
So that means having the right people, safety engineers, auditors, the internal expertise needed.
Exactly that. It's about having dedicated technical know-how in-house or readily available. They also have to show they can actually implement the SMS they've written down. Is it real? Are the processes working? It can't just be theoretical.
Makes sense.
Then they need evidence they've consulted properly about the SMS. Talk to the workforce, unions, other stakeholders who are affected by it.
And you mentioned proof. What about the money side? That seems like something people might forget until it's too late.
It's crucial. They have to show they have the financial capacity, either enough capital or adequate public risk insurance to cover potential liabilities if a major accident happens. Basically, ensuring the public isn't left picking up the tab if the worst occurs.
Okay, got the SMS, got the accreditation framework. But you said earlier, SSA isn't just paperwork. It needs real, deep organizational capability. You can't just, hire a consultant for a month to write a safety case and then wash your hands of it.
You've hit on a key point there, the difference between just being compliant on paper and actually being competent in practice.
Hmm.
To have that genuine safety capability, you absolutely need technical expertise in things like hazard identification, risk assessment methodologies.
Like HAZU, Bosch's and Foltry analysis.
Precisely. You need people trained in those systematic safety methods.
And it's not just about getting started right, it's about keeping it going, isn't it? Through the whole life of the asset.
It absolutely is.
Yeah.
You need systematic processes for managing change. Think about it. Most incidents don't happen when things are static. They happen during upgrades, when procedures change, when new equipment comes in. If your organization can't manage those transitions safely, that initial accreditation doesn't mean much down the track.
So you need dedicated people focused on integration, making sure the safety team isn't just off in its own little world. Who do they need to be constantly talking to?
Basically, everyone involved in the asset lifecycle. Design management, definitely. Engineering, operations, maintenance. If the safety assurance people only ever talk to other safety assurance people, the system is broken before it starts. And the final piece, which sounds obvious but often gets squeezed, is sufficient resources. Proper allocation. If you see a project manager trying to shave 20% off the assurance budget just to meet a cost target, well, that's a huge red flag. It signals that safety isn't being treated as the foundational requirement SFAIP demands, but just another constraint to be managed. Or worse, cut.
Okay, we've covered the legal side, the organizational setup. Now let's get practical for the engineers listening. How does all this policy and framework stuff actually connect to the design work? How does that SFA duty become, say, a specific requirement for a signaling system?
Right. This is where we bridge the gap. We link SSA directly into the systems engineering, the SE lifecycle. The crucial thing is SSA isn't something you do after the engineering. It has to be applied throughout the whole lifecycle of whatever change you're making. Its main job isn't just documenting safety, it's actively influencing safety outcomes, driving safer designs early on when changes are relatively cheap and easy.
And that implies a really tight, formal link with established systems engineering standards and processes.
Absolutely non-negotiable. The key connection is making sure you develop comprehensive safety requirements early in that lifecycle. SSA essentially translates the high-level legal duty, SMIRP, into tangible, measurable, technical safety requirements. Things like minimum safe braking distances or required levels of system redundancy or specific failure modes that must be prevented.
Okay.
And once you have those requirements defined, SSA then provides the framework to link them all the way through the design, build, and test phases, what we call verification and validation activities.
This sounds like traceability, the idea that you should be able to pick any component, like a signal light, and trace it back through the design documents to the specific safety requirement that demanded it.
Precisely. Traceability is fundamental. It confirms that every design choice impacting safety is a clear justification rooted in a requirement. And, maybe more importantly, it helps ensure no safety requirements get accidentally dropped or overlooked as the design gets more complex.
We often use the V model in engineering to visualize project life cycles. How does SSA fit onto that V shape?
The V model is a perfect illustration for SSA integration. Think of the left side of the V as definition and design decomposition, all driven by requirements, including safety requirements. You start at the top left with the high-level requirements phase, figuring out the operational safety needs based on risk analysis, stakeholder needs, and those SFA-RP principles.
Then moving down that left side.
You get into the design phase.
Yeah.
This is where those high-level safety requirements get broken down and allocated to specific systems and subsystems. You're deciding on the safety architecture. Will it need redundant processors, diverse sensors? That happens here. Then you hit the bottom point of the V, implementation, where things actually get built, coded, manufactured.
And then climbing up the right side of the V, the focus shifts completely.
Completely. The right side is all about confirmation, about assurance. You start with integration and testing. This is where verification happens, checking that the built components and subsystems meet their detailed design specifications. Then you move up to full system-level validation. Finally, at the top right, you have the operation phase, which involves ongoing safety monitoring and service and, crucially, managing any changes safely throughout the asset's entire life.
Let's pause on verification versus validation. You hear those terms used almost interchangeably sometimes, but in safety assurance, they mean very different things, don't they? It trips up a lot of people starting out.
They are absolutely distinct, and getting them confused is dangerous. Verification is essentially asking, did we build the system right according to the specifications? It's about checking the outputs of a design phase against the inputs. For instance, verifying that the software code for an interlocking system exactly matches the approved functional logic specification.
So it's like checking your homework, making sure you followed the instructions.
Exactly, an internal consistency check. Validation, on the other hand, asks a broader question. Did we build the right system? This is where you demonstrate that the system, once it's built and integrated with everything else, the track, the power, the signals, the procedures, the human operators, actually meets the original high-level safety objectives in its real operating environment.
Oh, so validation is more about the bigger picture, the interactions.
Precisely. Did putting system A next to system B create some unexpected hazard? Does the human interface actually allow operators to use it safely under pressure? Verification alone can't answer those questions. Validation, through testing, simulation, operational trials, has to.
That makes the difference much clearer. Okay, so given how complex rail systems are, SSA can't just talk to systems engineering. It needs to plug into other disciplines too, right?
Right.
What are those mandatory indication points?
Definitely. Beyond design management and SEC, SSA has to be tightly linked with RAM. That's reliability, availability, maintainability. They're all interconnected. If a safety-critical component isn't reliable, it directly impacts safety. So RAM analysis feeds directly into SSA.
Okay.
And critically, perhaps most critically in many modern systems, SSA must integrate fully with Human Factors Integration HFI. You can design the theoretically safest machine imaginable, but if the way humans interact with it is confusing or prone to error, it's not actually safe in practice. HFI has to be part of the assurance process.
When we're setting those safety requirements early on, we can't just say make it safe. We need concrete goals, right? Measurable targets. What does safe enough actually look like in numbers for something like rail?
Yeah, you need quantitative targets. We establish specific safety criteria. For example, if you're designing a new light rail system, a key target might be achieving a service availability of, say, 99.8% or higher. But beyond availability, you set targets related to the probability or frequency of specific hazardous events.
And these targets have to be realistic.
They must be achievable, yes. They also have to align with what the regulator expects, and they need to link up with those RAM targets we just mentioned. Reliability drives safety outcomes.
But the really tough conversation isn't just about service uptime, it's about the risk of actual harm. How do we draw the line between a risk that's acceptable, something we can manage, and one that's just intolerable?
That's precisely the role of the risk tolerability framework. It's a structured way, often shown as that kind of triangle diagram, to set formal numerical boundaries for different levels of risk. It gives you a practical tool for applying the SCRP principle.
Can you give us a sense of the numbers? What defines the top of that triangle, the really unacceptable zone?
Typically, the unacceptable risk level is defined by a threshold for individual risk of fatality. A common figure might be something like 5 times 10 to the minus 5 per person per year. So 5 by 10 year per year.
Which means,
To put that in context, if 100,000 people were exposed to that level of risk continuously for 10 years, you'd statistically expect about 5 fatalities among them just from that specific risk. That's generally considered too high for engineered systems. If your analysis shows a risk up there, you must reduce it, basically, regardless of cost. SFA 5 doesn't really apply in that zone. It's just no.
that's the absolute stop sign. Okay, what about the bottom of the triangle, the broadly acceptable zone?
Down there, the risk is considered negligible, so low that it doesn't warrant spending significant resources to reduce it further. The threshold might be around, say, 3 times 10 to the minus 7 per year, 3 by 10 year.
Yeah.
If your risk is below that line, you've essentially met the goal. It's acceptable.
And that big space in the middle, the ADAR region, that's where all the hard work happens.
That's exactly it. ALARP is low as reasonably practicable. Risks that fall between the unacceptable and acceptable lines land in this ALARP region. And if your risk is in here, you have to apply that rigorous SFARP justification. This is where you meticulously document all the possible control measures you could implement. You evaluate their effectiveness, their cost, their difficulty, and you provide clear, objective evidence for why you implemented the controls you did, and crucially, why you didn't implement others, proving further risk reduction wasn't reasonably practicable. Operating in LRP means constant justification.
Right, you're always demonstrating you've squeezed the risk down as far as realistically possible. Now, to actually build systems that meet these kinds of demanding targets, the rail industry doesn't reinvent the wheel every time. It relies heavily on established technical standards, right? What are the key ones engineers need to be familiar with?
Absolutely. Internationally, especially for electronic and electrical systems which dominate modern railways.
Hmm.
We rely heavily on the CNLX suite of standards. They're foundational.
CNLF.
Yes. So EN 5126 is a big one. It sets out the whole lifecycle management process for RAM's reliability, availability, maintainability, and safety. It's kind of the overarching management standard for how you handle safety throughout that V model we discussed.
Okay, the management framework. What about the specific tech software, for example?
That's where EN 50128 comes in. It dictates the extremely rigorous processes you have to follow when developing safety-related software, like the code inside a signaling, interlocking, or an automatic train protection system. And then EN 50129 covers the hardware side, the requirements for designing, building, and proving the safety of electronic systems themselves. It specifies the evidence needed for acceptance and approval.
And these standards often talk about safety integrity levels, SILs, SI1, SI2, up to SIL 4. How do those SIL ratings actually impact the design choices on a project?
SILs are fundamental. They classify how much confidence you need to have that a safety function will actually perform correctly when required. A SIL4 system, the highest level, is typically reserved for functions where failure could be catastrophic, like preventing train collisions.
Right.
Achieving SIL4 requires vastly different design approaches than, say, SL1. The standards mandate things like diverse redundancy, using different technologies to perform the same function, fault tolerance, incredibly strict configuration management, maybe even the use of mathematical formal methods to prove correctness. It's not just about using slightly better components. It's a whole different level of design rigor and proof required.
So SIL dictates the architecture and the level of proof needed. Beyond these international design standards, there are often national frameworks too, particularly for approving specific equipment before it's used. Can you talk about things like type approval, maybe referencing AS7702 as an example?
Yeah, national type approval frameworks like AS7702 in Australia are really important. They provide a standardized process for evaluating any new railway product, or even a significantly modified one, before it gets rolled out widely across the network.
What does that evaluation cover?
It looks at safety, obviously, but also performance, reliability, compatibility with existing infrastructure. It sets clear assessment criteria and defines exactly what information suppliers need to provide detailed test reports, materials data, safety analyses, manufacturing quality plans, etc.
And what's the big benefit for an operator or the industry in having this kind of standardized approval process?
The big win is promoting mutual recognition. Once a specific piece of kit, let's say a particular model of axle counter, goes through this rigorous type approval process and gets the stamp, the detailed documentation generated, often called product information packs or approval packs, can then be used by other rail networks. It helps avoid duplicating the entire costly approval process every single time that same product is used elsewhere. It streamlines procurement and deployment while still maintaining that essential safety rigor.
We know data is crucial for driving safety improvements. Historically, maybe safety efforts focus very heavily on the big, dramatic failures, derailments, major collisions, signaling breakdowns. But looking at the operational data we have now tells a much broader story, doesn't it? It forces a more comprehensive view of hazards.
It absolutely does. You have to look beyond the headlines. If you dig into overall operational statistics, the picture becomes much richer. For instance, while thankfully major accidents remain rare, you might see something like a 19.5% increase in total train incidents on the mainline network over a few years.
Okay, that sounds concerning.
It is, but then you look inside that number.
Right.
You might find that a huge chunk, maybe nearly 73% of the less severe, non-high-risk accidents are actually things like trains hitting animals on the track or striking debris, fallen trees, things like that.
Wow, 73% from hitting objects or animals. That really changes the focus, doesn't it? It tells engineering and operations teams that their hazard analysis can't just live inside the signaling cabinet or the train's braking system.
Exactly. You need a holistic view. It means considering environmental factors, animal controls, vegetation management, responses to extreme weather, dealing with trespassers and vandalism. These become critical safety requirements that need solutions beyond just traditional train control technology.
Yeah.
SSA has to capture and drive controls for these broader operational and environmental hazards.
And speaking of evolving challenges, we have emerging technology flooding into rail. This must be a huge area for SSA right now. Massive potential benefits, but also completely new kinds of risks and failure modes.
It's a massive dual-edged sword. Take AI and automation. They're moving rapidly into areas like signaling, traffic management, even predictive maintenance.
The potential seems huge.
Incredible benefits, yes. predicting component failures before they happen,
Yeah.
optimizing train movements to save energy and improve capacity. Fantastic. But AI, especially machine learning, introduces complex new risks. These systems can struggle with edge cases, situations they weren't trained on, leading to unpredictable, potentially unsafe actions. And they create new cybersecurity vulnerabilities. What if someone could deliberately manipulate the AI's training data or its decision-making logic?
Right, the black box problem. And then there's the Internet of Things, IoT sensors everywhere, digital twins modeling the entire railway in real time.
Again, revolutionary for monitoring asset condition, for planning maintenance, but inherently, these are network technologies. Every sensor, every connection point potentially expands the system's attack surface for cyber threats.
So a vulnerability in a simple trackside temperature sensor could somehow cascade.
Potentially, yes. If that sensor is connected to the wider operational network, could a hacker pivot from compromising that sensor to affecting a safety-critical system like the interlocking? It's a plausible risk that needs robust cybersecurity controls, which are now an integral part of SSA for any digital system. SSA processes themselves have to keep evolving to handle this new complexity, ensuring new tech genuinely enhances safety and doesn't just introduce new, poorly understood risks.
But no matter how sophisticated the tech gets, there's always a human involved somewhere. Maintenance, operation, control.
Absolutely. And human factors integration, HFI, is vital. But the focus within SSA here has really matured over the years. It used to be common after an incident to point to human error.
Right, blame the driver or the signaler.
Exactly. The modern SSA approach shifts that focus. Yes, human performance contributes, but we need to look upstream at the organizational factors, the systemic issues that influence that human performance. Things like poorly designed interfaces that are confusing under pressure, procedures that are unrealistic or out of date, issues with fatigue management, inadequate training. Those are the things SSA needs to address, rather than just blaming individuals.
So HFI needs to be baked in right across that V-model lifecycle, addressing those systemic issues.
Precisely. So in the design phase, HFI influences the design of control panels, displays, alarms, making them intuitive, reducing cognitive load, supporting safe decisions. During operation, it informs the development of effective training programs, realistic operating procedures. And for maintenance, HFI looks at things like ensuring equipment is designed for safe access, that diagnostic tools are usable, that procedures minimize the chance of errors during repair work.
Okay, so to wrap up that safety case, SSA needs to think about everyone who interacts with the system, all the users. Who's on that list beyond the obvious ones, like drivers and passengers?
It's a surprisingly long and diverse list. You've got passengers, obviously their safety, accessibility needs, clear information during disruptions. You have the operators, drivers, signalers, controllers needing systems that are usable, efficient, and don't induce fatigue or error. Then the maintainers, they need safe access, clear instructions, effective tools.
Anyone else?
Definitely. Think about emergency responders, police, fire, ambulance. If there's an incident, do they have the information and procedures they need to intervene safely without making things worse? And finally, the regulatory bodies themselves are stakeholders. They need clear, traceable evidence that the system complies with all the rules. SSA's job is to make sure the requirements of all these groups are captured, addressed in the design, and ultimately verified.
All right, let's bring this all together for the listeners, especially those just starting out on major rail projects. Based on everything we discussed, what are the real keys to making SSA work successfully in practice? What makes a project get it right?
You can usually boil it down to about 4 critical success factors. First, and maybe foremost, strong leadership commitment. Safety assurance has to be visibly championed from the very top. If senior management is seen to prioritize schedule or budget over resolving safety issues, that message filters down and the whole SSA effort gets undermined.
So it needs backing from the executive level.
Absolutely. Second, early integration. We've touched on this, but it's so important. SSA activities need to kick off right at the project conception stage, even before you've got detailed designs. Trying to write a safety case and justify decisions when you're already 80% through the build, it's incredibly expensive, causes huge delays, and often leads to major painful rework.
So safety planning starts when the business case starts.
Ideally, yes. Third is integrated planning. The assurance plan can't just be a separate document running in parallel to the main project plan. It needs to be woven in. Safety reviews, hazard analyses, testing phases, they have to be properly scheduled and aligned with key project milestones like design freezes or component delivery.
Makes sense. They depend on each other.
And finally, competent resources. You simply have to allocate enough people with the right skills and experience to do the assurance work properly. That means people who understand the engineering, yes, but also who understand safety assessment methodologies, standards, and regulatory expectations. Skimping here is a false economy.
Okay, those are the success factors. Now let's flip it. If you're managing a project or part of a project team, what are the common pitfalls? The warning signs that your SSA process might be going off the rails, so to speak.
Unfortunately, we see the same mistakes repeated quite often. The biggest one, probably, is underestimating resource allocation. People consistently underestimate the sheer amount of effort involved in thorough safety assurance, especially the documentation, the hazard analysis workshops, the independent reviews, the testing. Projects often don't budget enough time or money, leading to rushed, superficial safety cases that simply won't pass muster with the regulator.
And the regulator isn't going to bend just because your project deadline is looming.
Not a chance. Which leads to the second common pitfall: poor timing coordination. Failing to properly sequence those critical SSA activities with the main project timeline, you end up with bottlenecks. For example, you can't realistically start system integration testing if the safety requirements for those systems haven't been formally defined and approved through the SSA process first. It causes delays and frustration.
The third one feels like it could be a really technical challenge on big projects with lots of different parts.
It often is. Interface management. This is about inadequately defining and assuring the safety of the connections between different complex systems, or worse, between the scopes of different contractors or organizational departments.
Like the classic wheel-rail interface.
Exactly. If contractor A builds the train and contractor B builds the track, who has the overall responsibility for assuring that critical wheel-rail interface safety? If that's not clearly defined and managed through the SSA framework, massive risks can fall through the cracks.
And the final pitfall seems to circle back to what you said about genuine capability.
It does. It's about competence development. Organizations sometimes fail to invest sufficiently in building up their internal SSA expertise. They might rely too heavily on consultants, or their existing team might lack the skills to grapple with new technologies like AI or complex software systems. If your safety auditors only really understand traditional relay-based signaling, they're going to struggle to effectively assure a modern, software-intensive system. The capability has to keep pace with the technology.
One last point on implementation. SSA isn't just about getting the system into service. It's not a one-and-done activity, is it? What happens when that system needs changing 5, 10 years later?
That's absolutely critical. SSA has to be fundamentally embedded within the organization's ongoing change management process. Any modification, no matter how small it seems, a software patch, replacing a type of track component, changing an operating procedure, must trigger a defined SSA workflow.
What does that workflow involve?
It typically includes an immediate impact assessment. How might this change affect the existing safety arguments and evidence? Then, a risk reevaluation based on the proposed change. You need control verification. Do the existing safety measures still work, or do they need adapting? And, of course, thorough documentation updates. The safety case must always reflect the system as it actually is. Safety assurance is a continuous life cycle commitment, not a static document you file away.
So if we try and wrap this entire deep dive up, the fundamental message seems clear. System safety assurance isn't just some bureaucratic hurdle, some compliance task forced on engineers by lawyers to slow things down.
Not at all. When done right, it's a core business practice. It's fundamental to protecting people, obviously, but also to safeguarding billions of dollars worth of assets, protecting the organization's reputation, and ultimately it's what enables rail services to be sustainable, efficient, and reliable in the long run. It really shifts safety from being seen as just a cost or a constraint to being an active enabler of business value.
Okay, let's leave our listeners with a final thought to chew on. We've talked a lot about how new technology, AI, automation, complex software, networks of sensors is rapidly increasing the technical complexity of rail systems. It's introducing new failure modes, maybe subtle ones, things like algorithmic bias or vulnerability to cyber attacks that are really hard to fully predict or test for. We can build these incredibly complex systems, but here's the question. How do we make sure that the competence and the capacity of the organization, the human experts doing the SSA, auditing these systems, making those crucial LRPO judgments, can actually keep pace? As the systems get exponentially more complex, what new skills, maybe blending traditional engineering with software expertise, cybersecurity knowledge, data science, even ethics, what skills will be most critical in, say, the next 5 years to ensure the human assurance element stays ahead of the complexity we're creating?
That's something to really consider as you approach your next project. or even your current role. Think about how you ensure safety isn't just treated like the roof you add on at the end, hoping it fits. It really has to be that solid, non-negotiable foundation, poured and checked right at the very start before you even think about designing the first wall.